All right, so today we continue with neural networks, but before we get into this, yesterday there was a question about the matrix representation of I'm guessing it's your input data, and Adina, if this is not if this is not what you were asking about yesterday, let me know. I'm assuming it's this. Okay, perfect.
Thanks.
So this is really just a breakdown of how you can take image data and represent them as like a single row of data. As you can see here, what this is doing is you're taking each of these layers, unraveling them, and then just putting them all in one dimension so that you can feed it into your neural network. The thing that I assume is throwing people off is here. Each column becomes a row of data, or each column is an image, and then each row becomes a particular pixel in the data. I will say that if you go to the next lab, I don't think the matrix is in this format. I believe it is actually, the normal way of like your rows and columns. Yesterday, the neural network that we dealt with was also rows and columns. I don't think, this is not one of the, I would say this is not a big thing to like harp over. But yeah, it is pretty counterintuitive that like each column is an observation and then each row is a pixel, or like, yeah, a third of a pixel. I think the main point here is showing that how you can represent a full image that, is 2D, or you could say even 3D, because there are 3 layers of colors here, as, a single vector. This representation, I will also say, because we are going to get into convolutional layers later, this would be if you want to feed your image data into a neural network without convolutional layers. We'll take a look later. Convolutional layers, you can actually keep your images in this format of like a tensor, just because it is important where the order of your pixels and like, where the next row of pixels begins. So we'll see that in a little bit. But yes, just to clarify, you would turn your images into this shape, a single vector, only if you don't want to use convolutional layers. For those of you who have indicated interest in doing an image classification project, you don't have to use convolutional layers. They do take longer, but tend to have more accuracy because of its ability to detect like lines and patterns or like textures in images. But yeah, it's up to you. It is in the what I'll be talking about today with convolutional layers is in the appendix. So if you don't want to include that in your project, because the models do take much longer to run, I'll actually show like a really simple example later. You don't have to, and you can definitely save that for like maybe the capstone where you have more time to wait for a model to run. Anything else to clarify with this notation? All right. Well, today you can see we have quite a good bit to get to. I'm going to keep a watch on the time, because all of these tuning things, if we like are running out of time, I'm actually going to cut off the tuning parts and continue tomorrow, because I do want to talk about the more like image specific stuff today. So I'll keep a watch on time. But most of today, what we'll be talking about is tuning the different parts of neural networks. And then I'll get into all the images. So before we begin, any other questions that maybe you want me to touch upon? All right. So I'll be referring back to this, which is what we did yesterday. This was our sequential model that we built, really, really simple. It only has a single hidden layer with 12 nodes and one output layer that does a binary classification. So I'll be referring back to this as we talk about the different things to tune. So tuning neural net parameters is difficult, just because it's hard to figure out. It's hard to not figure out, but it's hard to foresee what patterns your neural net will learn from your data. it could be because of, the random initialization of your weights at the start that lead it to go down specific rabbit holes, or, in just like the different directions that, or the different nodes and different combinations of your nodes that your data is moving through, it can really, yeah, it's really hard to foresee what is learned. So usually when you're building a neural net, you're just going to test a bunch of different options. So we'll start with something simpler and then we'll build on this. So the first thing, and let me just make this a little bigger. The first thing we'll talk about is adding nodes and layers. So yesterday, I believe Melody had asked the question of what's the difference between adding nodes versus adding layers. Let's start with adding hidden layers. So to add a hidden layer, I think I did a quick example yesterday, but to add another hidden layer, all you have to do is just add another one of these. So you can literally honestly copy and paste this. Future hidden layers don't need the input dimension just because it knows that it's not an input layer. And we'll talk about activation functions later. It can be the same, it can be different between your different hidden layers. So with the hidden layers, for a lot of what I'm trying to say, narrower data frames, like if you don't have too many columns, you can start with just one or two of hidden layers and it'll work just fine. For more complex problems, you can gradually ramp up the number of hidden layers until your model starts to fit or overfit. Typically, because you don't want to add unnecessary layers. I think I also alluded to yesterday that adding more layers will lead to overfitting just because you get more intricate with your decision boundaries. So the usual structure is, just add layers as you go. So very complex tasks like image classification without convolutional layers usually need dozens of layers, because you imagine if you have an image, even an image with like 28 by 28 pixels, which I think is the dimensions that we'll be dealing with later on. Think 28 by 28, that's like roughly about 900. That's already 900 columns. If it's a color image, you multiply that by at least 3, sometimes 4. That becomes 2,700 columns. You can imagine how much information you're feeding into your neural network. The more layers you have, the more intricate things your network will be able to detect. Kind of similarly, the number of neurons per layer. So the number of neurons for your input and output layers is dependent on your data and the task. So remember yesterday, this was our input layer. Our input layer had a dimension of 8 just because we had 8 columns. We'll see with convolutional layers, you also have to feed it in that information. And then your output layer as well. Your output layer usually is just one node that does the full aggregation. So yeah, your input dimensions are determined by your number of columns, and your output layer for classification, as an example, has just one node with a sigmoid activation function. For hidden layers, a common practice is to create a funnel with fewer and fewer neurons per layer. So you usually want to start with a lot and then slowly take it down. So I think if you look up like common neural network, I don't know, images, they usually have a funnel shape. But in general, you'll get more bang for your buck by adding more layers versus adding more neurons. So if you find that your model's really not learning anything at the moment, your first step would be to add more layers. In terms of number of neurons per layer, that is a difficult question to answer. Again, it does depend on the number of columns that you're feeding in. It is pretty normal to just try different numbers of neurons in your layer, but to see a more significant change or improvement in your model, you might as well just add another layer. Questions about this?
Is there any specific way to determine how many units in each layer we should have? For example, 10% of our input data, something like that.
I will say no. If you start with a fairly large number, I would say you would tune the number of, let's say you start with one layer first. That's when you can maybe tune the number of neurons that you want. And then when you find that that's not improving by much, you might as well add a layer afterwards. So it's hard to say. I will say like the number 12 that I have here it's arbitrary. So I would say maybe have it based on how many columns you have. You always want to have more nodes than inputs, I think. But that's also not always true. So yeah, I have no direct answer to that. I would say just something that I've done in the past as well, is to try different numbers. Oh, and yeah, just so to point out, to change the number of nodes in each hidden layer would be the first argument here. And in this case, both of mine have 12 nodes.
So for an image where you said like you might have 9,000 columns, you would literally have 10,000 nodes in each layer?
Yeah, that is very, very possible. And yeah, if it's an image with like 9,000 columns, your input dimension would be 9,000 as well. Anything else before we talk about the next thing? All right, let's move on to activation functions. So there's a lot that you can go into with the theory of activation functions. I'm just going to talk about some of the more common ones. These are the shapes of activation functions. You can see functions like sigmoids and hyperbolic tangent, they bound their values. So they're often used for classification problems that, your probability is bounded between, a 0 and a 1 as an example. One important thing to know for activation functions is its derivative, the differentiability. Just because if any of you have gotten into some of the videos that I sent out yesterday on backpropagation, the derivative of the activation function is actually used as part of the optimization process. So yeah, some really quick examples. Examples for output layers I'll talk about first. So your output layer activation function is what determines, the bounds of your output of your neural network. So really standard ones to go for: binary classification. You would use a sigmoid activation function in your final layer. So if we take a look at this example again, whatever your last layer that you're adding is, one, make sure that you only have one node, but that your activation is sigmoid if you're doing a classification problem. For multi-class classification, the most common one I believe is softmax. You would literally just change this into softmax, and it would give you a non-negative vector that sums up to 1. So for example, if you have 5 different classes, you would get a vector that consists of 5 different probabilities of that data point belonging to each class. And then for regression problems, you can actually feed in a linear function or ReLU activation, because both of these functions, well, you can see here, this is ReLU and the shape of ReLU. It is pretty much linear for any positive values, or linear. So linear would just be, instead of it being flat here, it'll be straight all the way down. So you use this for regression one mainly because it is unbounded. So this is for the output layers. These are the most common tasks. I will say if you're doing something different, like if you were creating like word embeddings, or if you're creating, I don't know, any sort of vectors to represent your data, your output layer will not consist of, oops, where was that? Yeah, your output layer typically won't be just one node. You can have however many nodes depending on how many dimensions you want your output vector to be. So that's also something that's pretty common. Sometimes for this can be used for like recommendation algorithms, or recommendation algorithms. By that, what I mean is, let's say you want to make a recommendation system and you want each item to have like a vector that you've trained on something. You can have a vector output from your neural network. I'll get more into that probably if people have questions about it during office hours or in the capstone. I can talk about some examples of incorporating this with recommendation engines. So output layers, pretty much if you were to Google, I'm doing a classification problem, what activation function should I use? These are the standard ones. So activation functions for hidden layers is a little bit less obvious. I've linked a couple articles here that walk through, you know, why certain activation functions work better in certain scenarios. First of all, sigmoids, even though we always use them as the output activation function, they're not often used in hidden layers. And the idea behind that is that the derivative value, this maximum derivative value of a sigmoid function is pretty small. And the idea of this is that it only propagates a small amount of error each time, leading to very slow learning. This small derivative, therefore slow learning issue, is known as a vanishing gradient problem. So if you ever see an activation function that has this vanishing gradient problem, usually it just means that it's a very slow learner and not much error gets propagated through the neural network. So yeah, this is just terminology to just be familiar with some of the phrases that are used in the neural network space. Another very common, I would say more common than sigmoid function that is used is tanh, hyperbolic tangent. Mathematically, actually, it's very, very similar to a sigmoid function. So it also kind of has the vanishing gradient issue, but not as bad. So sometimes you might want to constrict your learning rate to have it learn slower so that, you know, you can pick up more intricacies, take a longer time to learn, but you have more accuracy. But yeah. But I would say the most common activation function used for hidden layers is ReLU. And it basically has to do with its gradient always being 1 as long as the input is positive. So because of that, you get the full error propagated back into your neural network. But also, as you can see with this function here, if your value is below, if your value is negative, if your input is negative, your output will be 0. And that sort of helps with helping your neural network run faster, because any negative input just won't be considered. This is also known as your neural networks not firing. So yeah, it just ends up being a little bit faster overall. So yeah, you can see here, negative inputs going to 0 can make your network lighter because no weights or biases will be updated if the input is negative. With these activation functions, there's a lot of reading to be done. And if you want to fully understand, you know, how different activation functions will affect your backpropagation or your training of your neural network, very, very important to get into the theory of it. Unfortunately, you can't skip the math to understand how that works. So just so you all know. Questions about activation functions?
In ReLU, when it is 0, it means that the weight is 0. It becomes 0. Or...
Oh, it means that. So let me go to do I have a picture of a neural network here? Let me see. Let me pull up yesterday's one real quick because that one has an example. Here we go. So let's just use this. So if this sum is negative, it'll output 0 out of the node. So it actually sums the weights from the previous layer. When it gets into that layer, when it gets into like that ReLU node, it will output 0. Does that help?
Yeah, okay, thanks.
You're welcome. Going back to like where you do this, with each hidden layer, you can, or with every layer, you can define what activation function is being used. So here, we're just using ReLU. The others, there's a lot of different activation functions too. So in these articles, there are like really quick explanations for why you do or don't want to use certain ones. All right, the next thing to talk about is loss functions. So loss functions are pretty much the same as cost functions, the cost functions that we were trying to minimize in gradient descent. So for example, you know, RMSE for linear regression or Gini or entropy for trees. For different issues that you're trying to solve, you want to use different loss functions. So for example, for regression problems, if you are trying to do a neural network regression, Keras actually has mean squared error or mean absolute error as a loss function. These are pretty much the same thing as RMSE. Well, same idea as RMSE. Or this one's pretty cool. I actually found this one a couple weeks ago. If your target has potential outliers, there's also mean squared log error. So it actually will not add a lot of error if you have big outliers. So that might be helpful if you feel that your target might have outliers. Just something to try. For binary classification, you have binary cross entropy. For multi-class problems, you have categorical cross entropy. Conceptually, it works very similar to the decision trees cost function, basically like how much purity is there, but it's not computed in the same way. There are explanations of how that works exactly. Where you do loss functions, because your loss function is computed over your entire neural network. So it is in the compilation step. So when you're compiling your model, you tell it what loss function it is in that step. So yeah, in this case, because we were doing a binary classification, we put binary cross entropy here. Questions about loss functions? All right. So with loss functions, there are also different optimizers. And as you saw here, I used the Atom optimizer also in the compilation step. This optimizer is basically how the model finds the optimal parameters. And I think I say that over here. Yeah, so different optimizers are just different methods or paths that your neural network can take to find the optimal values. Experimentally, Atom, and the name is actually Atom. The creators of Atom actually said it's not an acronym. The name of it is just Atom, is a good one to use. So as a quick optimizer summary, and Atom is a combination of the first two. RMS prop is one of the classic optimizers, and it maintains per parameter learning rate. So it adjusts learning rates across different parameters, adapted based on the average recent weight updates. So if you see that, all right, this weight changes a lot, maybe the learning rate can be a little bit faster. And this does well on non-stationary problems. If you have a lot of noisy data, it has adaptive learning rates because of that. AdaGrad is actually similar to RMS prop, but it improves performance on problems with sparse gradients. Sparse gradients just means if your data is very, very sparse. So you imagine in NLP, if you have like a TF-IDF model, remember there's a lot of zeros in our inputs. So AdaGrad, if you have very sparse data like that, AdaGrad usually works well as well. And computer vision is like object detection. So that also typically has pretty sparse features. And finally, Atom has the benefits of both AdaGrad and RMS prop. So again, that's why people tend to use Atom. Instead of adapting parameter learning rates based on the average first moment, so basically what RMS prop was doing, Atom also makes use of the average second moments of the gradient. So basically looks at, all right, is there a variance in the way that my weights are changing? And then it just adapts learning rates to optimize for that. So it's taking a lot of the changes in your weights into consideration. I would say with either of these, you will get to your optimal values eventually. Just in some cases, some of them will work faster than others. And because neural networks are so complex, getting to your optimal values fast as possible is important. So these different optimizers, you will get to your same or very similar values eventually, but it's just a matter of how quickly you get there. How many epochs does it take for your neural network to learn the optimal values? Questions about optimizers? All right, and yeah, optimizers, I think I just said you will define your optimizer within the compilation step. All right, so a couple more to go before we talk about images. Learning rate, and learning rate, you really only specify the initial learning rate, just because these optimizers do adjust your learning rates as it trains. So yeah, it's something that you can define when you compile your model with the optimizer. So I don't have it in here, but you can also add, and I believe it's called initialize. I forget what the name of the parameter is, but there is a parameter that you can tell it what you want to initialize your weights as. But yeah. So optimizers usually change up the learning rate. So this is just your initial learning rate. Just things to keep in mind. If you set it too low, your training will eventually converge, but it'll do so slowly. So same principle as gradient descent, right? If your learning rate is very, very small, you will get there, but just slowly. If you set it too high, you might diverge. You might end up, I guess, underfitting your data. So if you see that, you know, your the graphs that I had yesterday, if you see these graphs not converging at all, you could have had a learning rate that is too high. And if you set it slightly too high, it's possible that it would converge first and then just miss your local optima. So basically, that's why it's important to look at your over the number of epochs, your either your loss function or your accuracy, just to see, you know, is your model getting there, or did it get there and then lose its way? So yeah, those are things to consider. If you see weird patterns happening, if you don't see that it's nicely converging, it might be a learning rate issue. Questions about that?
What is the difference between learning rate and optimizers? For example, in Adam optimizer, we can learn faster, right?
Mm-hmm.
But is it different from learning rate?
Yeah, so they kind of are, they're kind of interconnected. So learning rate, you set that at the very, very start, because, you know, you have to have some initial learning rate at the start before these optimizers figure out the best learning rates. So it's kind of, they are connected. So yeah, so the optimizers will adapt to learning rates based on your learning rate that you give at the start. Does that make sense?
Okay. Yeah, thank you.
You're welcome. Anything else? All right, well, the last thing we're going to talk about, and I think some of you have asked me, like, don't neural networks tend to overfit because of how complex it is and of how much, like, because of how much intricacy you get with it learning data? Yeah, it does tend to overfit a lot. Therefore, regularization becomes quite important. So something to be aware of is, as a neural network learns, the weights will settle into their context within the network. So weights of neurons will be tuned for specific features, providing some specialization. So for example, and this is just like a really, really high level, maybe you have 10 neurons. The first two are focused at, in the context of images, for example, the first two will be focused on, all right, let's take a look at color. The second two maybe will be like, all right, let's take a look at textures. Are there specific like patterns in an image? Maybe the third two will look for edges. Are there hard edges, soft edges? Maybe the directions of most lines in your picture, stuff like that. And that's what you mean by specialization. Neighboring neurons might become too reliant on a specialization. You can think of this as literally overfitting, which if taken too far can result in a fragile model too specialized to the training data. So another term that is used kind of often is this reliance on context for a neuron during training is referred to as complex co-adaptation. So if anyone says there are complex co-adaptations in your model, it just means that it's over-learning certain things, and therefore you want to introduce some regularization. And regularization, there are different methods, but it's pretty much the same principle as regularization we were talking about before. Basically introducing some slack in your model such that it doesn't overlearn anything. And there are a couple different methods to do this. So within each hidden layer, you can actually add a regularization parameter, and L1, L2, exactly the same as we were talking about. Well, not exactly the same, but in the same kind of concepts as we were dealing with ridge and lasso. So L1 just introduces a penalty term, and L2 introduces that with a squared. And you can introduce that within each hidden layer. I believe, I don't have an example here, but you would introduce another parameter within each layer. So you can do that, which we're already familiar with the concepts of L1 and L2. You can also add a dropout layer. So dropout layer, I'll get into a little bit. And also, this is not technically regularization, but you can also introduce early stopping so that your model doesn't overtrain. So early stopping is actually a good time saver. If you like got your model to do like 1,000 epochs, but it's already started to overfit at like epoch number 600, you can tell it that, all right, if I'm not seeing any dramatic increase, or if my validation accuracy is starting to go down, you can have your model just stop training and use the weights at epoch like 600, for example, instead of letting it overfit to 1,000. So I'll show some sample code in a little bit too. So talk about dropout. Dropout is a technique where randomly selected neurons are going to be ignored during training. So they're dropped out randomly. Like your neural network will literally not use several neurons just randomly. So this means that their contribution to the activation of downstream neurons. So if you have like one layer and then you introduce a dropout layer, your next layer will only train or update the weights of like half of the neurons. So yeah, the contribution to the activation of downstream neurons is temporarily removed on the forward pass, and any weight updates are not applied to the neuron on the backward pass. So you can add dropout layers in your neural network. So yeah, just like how Thanos, well, he didn't do that, but similar idea. So some quick code, you can see that if you want to add a dropout layer, is as simple as just doing model.add dropout 0.2. You do have to import the dropout layer from Keras, but 0.2 means that you're gonna drop 20% of your neurons in the next layer. Sorry, 20% of the inputs that go into your next layer. And then for early stopping, you can import it from Keras as well. Something that's pretty cool is you can also introduce a patience parameter. So basically, how many epochs the model will keep running until you stop training. So basically, early stopping will look out for, all right, is my validation going down? I will wait 2 more epochs before I stop, just in case it just happened to go down by however much you define. So yeah, those are different regularization techniques. I think we're pretty good on time, but yeah, any questions at this point?
Yeah, question about your phrasing about regularization. When you say you add it to each layer, does that mean you add it to every single layer, or you choose each individually?
You can choose. You can choose.
Okay.
It's to the point of like you can add like I could add a L1 to this layer, an L2 to this layer. Yeah, you have that flexibility. Anything else? Cool, awesome. I know some of you are excited for this. So let's talk about convolutional layers. So convolutional neural network, abbreviated as the CNN, is a neural network that just includes convolutional layers. And we'll take a look at what those mean in a little bit. So CNNs are mainly used for image recognition or classification, and they can be used for video analysis, NLP, like sentiment analysis and topic modeling, as well as speech recognition. Mostly, and the easiest application of CNN is images because it's obvious to see how it works, and we'll take a look at that later. So first, drawing a comparison between how we see images versus how computers see images. So how do our brains see an image? So in detecting, all right, is this a dog or a muffin? You might look for, all right, are there tails? Are the noses wet? Do you have flappy ears? Is it a good boy? And we conclude that we're probably seeing a dog. There is not one singular thing about a dog that our brain recognizes as a dog, but it's a combination, an amalgamation of different patterns that allow us to make, a probable guess. There are like a bunch of these images that have like food items that look like animals. And yeah, you can imagine that, like, I don't know, they do look kind of oddly similar. So moving on from this, how do computers see images? So to computers, color images are a 3D object composed of 3 matrices. One, here, let me scroll down a little bit. One for each primary color that can be combined in varying intensities to create different colors. So basically, every pixel that you see has some intensity of blue, some intensity of green, some intensity of red. In some images, I believe, I forget if it's like PNG specifically, but some images you might have a fourth layer, an alpha layer that basically tells you the transparency of your image. If I'm wrong about that, let me know, because I'm not an image. I don't know what the alpha, but anyways. So each element in the matrix will represent the location of a pixel and contains a number between 0 and 255, which indicates the intensity of the corresponding primary color in that pixel. So to a computer, this is what images look like. So how do you translate this to, is it a dog or a muffin? So we use a convolution layer. I will also say, I don't think I say this here, but I will say that you can also do a neural network for images without convolutional layers. So, oh yeah, I think I said that at the start. So yeah, just to reiterate, if you want to do a CNN project for this phase, you don't have to use convolutional layers because they tend to take a much longer time. And also usually you need, a bunch of layers. So yeah, it'll take a long time to run. But usually with a convolutional layer, you have the added bonus of, detecting patterns within your image. And we'll talk about how that works in a little bit. So convolutions. To convolve just means to roll together. CNNs really just make use of linear algebra to identify patterns using the pixel values. And they do this by taking a small matrix and they move it across an image. So you can see what's happening here. Imagine this is our image. The convolutional layer, you're just taking a smaller image and you're just looking at it like 9 pixels at a time in this example. And then the convolutional layer, so this smaller matrix, you can see here that has values of like -1, -2, -1, zeros across the center row, and then 1, 2, 1 at the bottom. This image will probably try and detect, are there edges? Because if you're trying to like multiply, negative zeros and positives with that pattern on a convolutional layer, you can sort of see if you can detect horizontal edges. But yeah, this small matrix, oh wait, I don't think I read this yet. So yeah, you multiply it every time it moves. So basically you're multiplying pixel by pixel, and that's what these bigger numbers end up being. And so from this, our network will mathematically try and identify patterns in these images. Just as terminology, this small matrix is known as a kernel or a filter, and each one is designed to identify a particular pattern in an image. These numbers are not something that you define. This is actually also tuned in the backpropagation process. Any questions about this so far? And so the advantage of using a convolutional layer over, just stringing all of your pixels into one long vector is you can actually see like clumps of pixels instead of, if you have everything in one long vector, it's hard to tell, all right, what pixels on top of what pixel. But with a convolutional layer, you can, just because it maintains the 2D representation of an image.
Excuse me, after filtering, we have, for example, an image that has pixels higher than 255.
Yeah, so this, technically, yeah, you can end up with images that are outside of the range of 0 to 255. Again, this is not another image, but it's just like some numerical representation of the image throughout the layers of the neural network. That makes sense?
Yeah.
Okay, awesome. All right. So yeah, after this filter is rolled over the image, the resulting matrix here, it's called a feature map. So it's not another image. And it's literally a map of where each pattern of feature is in the image. So for example, this would just be some representation of like, where are all the horizontal lines in the image. So elements with higher values indicate the presence of a pattern the filter is looking for. And yeah, the values or weights of the filter, as I mentioned earlier, that's what's being adjusted during backpropagation. So yeah. So some additional parameters with convolutional layers. One thing that you can introduce in your convolutional layer is padding. And padding is kind of similar to what's happening here. It's convenient to pad the input volume with zeros around the border. And it just really helps with detecting patterns at the edge of an image. Just so that, you know, imagine these three are the center, or let's say this 75, 75, 70, that's the edge of the image. It just allows it to be passed through other parts of the filter. So maybe if there's a vertical edge, you're able to detect that there. So that's padding, just adding another layer of like zeros around the edges of the image. And then there's also stride. And stride is just the number of pixels to shift the filter on each roll. So the larger the stride, the smaller the feature map will be, but we lose more information. So this is having a stride of 1 because it's only shifting by 1 each time. And as it goes down different rows, it also only shifts by 1. If you have a stride of 2, it will shift 2 blocks at a time. And therefore, if it shifts by 2, I believe it'll only take, let's see, 1, 2. It'll only have a feature map with like a 2 by 2. It'll only have a 2 by 2 feature map. So yeah, questions about this? These are things that you also get to tune in your neural network. All right. So along with convolutional layers usually come with another kind of layer known as pooling layer. So after a convolutional layer, the feature maps are fed into a max pool layer. So like convolutions, this method is applied one patch at a time. It has the same like shifting idea. And max pooling just takes the largest value from one patch of an image and places it in a new image, new matrix next to the max values from the other patches. So you can see here, we have a 2 by 2 filter and a stride of 2. So in this 4 by 4 image, you're just going to get 4 values. And literally what it's doing is just taking the maximum value from each. And yeah, it just discards the rest of the information contained in activation maps. So other methods exist, such as like average pooling. So this is just taking the maximum. So again, more options of layers to add. So what this is used for, it results in a new feature map with reduced dimensionality that is then passed into another convolutional layer, continue the pattern finding process. So these steps are repeated until they're passed to a fully connected layer that proceeds to classify the image using the identified patterns. So in a convolutional neural network, you're doing multiple layers of convolutional layers, pooling layers, convolutional layer, pooling layer. And as we'll see later, you are going to feed it into dense layers. And that's what you have to feed it into to, you know, because your output is going to end up being like a value or a one-dimensional vector. So after this pooling layer, the next thing we have to talk about is flattening. So that's basically the process of getting it from a 2D thing to a 1D thing. So once a neural network has collected a series of patterns that an image contains, it's ready to make a guess as to what the image is. So in order to do so, it flattens the 2D matrix into a 1D vector so that it can be passed into a normal, densely connected layer for classification. Then using this vector, one or many densely connected layers will be able to make a prediction as to what the image is. And I do have an example of a CNN, but at this point, any questions about, you know, these new layers? Cool. Something else to mention, with these layers, all of these other tuning methods do still apply. So you can change the number of, actually, no, we'll talk about that when we have the CNN example. But yeah, you can basically tune all these layers in the same way you were tuning the dense layers from before. All right, so in this example, we're going to be building a really, really quick image classification problem using this pre-built data set called CFAR10. And yeah, as an example, and these are very, very small images, and you'll see how long it takes to run even on these really tiny images. So these are color images. If we take a look at the dimensions here, so these are just some examples, and these are the dimensions. You can see that in our train set, we've got 50,000 images that are 32 by 32 pixels wide. And then this 3 is just saying that there's 3 layers of like the red, green, and blue. So this is really the dimension of our image, of a single image. And then our Y, 50,000 values of like, and in this case, sorry, I didn't mention, there are actually 10 classes in this data set. I think, oh, I linked to an example that walks through a better version of this. I just don't have time to run the entire code, but I did link down here to a work through example using the same data set. You'll see how many layers that they've added. So yeah, this is going to be our data set, and we're just going to do a very, very simple CNN. You'll see the results are not great. I don't know if they're actually run by the time we're done, but let's just quickly, you should do some EDA before. With images, it's a little harder to do EDA, but you can do things like most salient colors, most salient like pixel values. But yeah, at a very simple level, you can see that this data set is balanced. It has 5,000 images from each of 10 classes. And the classes are like, I don't know, let me see if I can find it here. There we go. We have airplanes, automobiles, different animals, and then also a ship and a truck. These are our categories. Going back to this, let's take a look at our CNN model. So this is a very, very simple CNN model. Here you can see, again, it's a sequential model, and sequential just meaning that it is a forward feeding. We're not really going to do any sort of like, I don't know, your data just flows through the neural network in one direction. Here you can see what I'm doing here. Let me just separate the different parts so it's a little clearer. So first of all, I'm making my first layer be a convolutional layer. Usually your first layer will be a convolutional layer because that's when you want it to detect, you know, the patterns across your image with that filter. So it has 64 nodes with a 3x3 filter. So this is what these numbers are. The activation functions, same ones as the ones we were talking about with the dense layers. And this, you have to define the input shape of your image. So here I'm just telling it 32, 32, 3, and I get that from here. So you can see here that I'm just doing like a very, very standard CNN structure, convolutional layer followed by the max pooling. Of course, there's also average pooling, but I'm doing max pooling over here. Oh, this also is for 2-dimensional images. There's also 3-dimensional ones, but I've actually never used them before. But yeah, here you can see I'm doing a 2x2 pooling layer. And then after the pooling, I'm going to see if it can detect any patterns from the pooled layer. And that's what I'm doing here. Again, I talked about a very, very common structure being the funneling. So I just lowered it down from 64 to 32. And I'm using these numbers just so it wouldn't take that long to run. You can use much bigger numbers. Same activation function, and again, followed by a pooling layer. After this, the convolutional layers, I'm going to just flatten my vector, flatten my image into a vector with this step, and then just feed it to one more dense layer, followed by my final layer, which, as you can see, because there are 10 categories here, I'm using the softmax activation function. When I compile this, categorical cross entropy is the loss function used for multi-class classification. I'm just using the SGD optimizer. I'm not sure, I guess just an example of a different optimizer, and I'm focusing on the metric of accuracy. Again, you can also put in recall, precision, F1. So with this, I'm going to fit my data, and this is actually the same process that we talked about yesterday. But I'm fitting my data. You can see that it does take a good bit to run. I only have 5 epochs, and you'll see that the accuracy is getting a little bit better over time, but the loss function is a NaN value just because it's not really predicting well at all. But yeah, as this goes, I'll let this keep going. You can actually plot the, this is going to be the overall, I believe the overall accuracy and loss. And then we'll take a look and see what these plots are. Hopefully it runs by the time this is done. But yeah, any questions right now?
We have a lab in our lessons that says that if your loss is NaN, you have to normalize your input with your output.
That makes sense, yeah.
Yeah, how we should that in images?
So I don't have it in here, but basically from Keras, you can get this image. It's called an image generator object, and you can actually normalize all your features. And so as you can, if you see like, I guess I don't have the pixel information here, and this is running, but the pixel values are going to be between 0 and 255. So a very common thing people do is they'll just take all of this and just divide everything by 255 because you know that your data is bounded. So yeah, that's something that that you can do here. Just there is a built-in way to do it through Keras and the image generator. I believe it's called image data generator. In the CNN labs, they should have it there. If not, let me know. But yeah, in that you'll be able to scale your image. Let me see if I can actually right now grab a really quick example. Let's see here. Oh, and any questions, right? Any other questions right now as I look for this and as that CNN is running?
So how many layers is this neural network?
So this neural network is, I think, 6, 7 layers. So 1, 2, 3, 4, 5, 6, 7, 7-layer neural network. Anything else? I think I just found. I'm gonna actually pull up one of my past projects that I know uses this image generator object, and hopefully, I do hope it loads.
And also in convolution, we can use dropout regularization or not?
In convolution, yes, you can. You can use dropout. It would just be another layer. I don't know what, honestly, I'm not too sure what the implications are if you put dropout, like if you put a dropout like between, like after this layer or after that layer. Honestly, not too sure. I don't think I've played around with that enough, but yeah, you can definitely add a dropout layer with convolution.
Okay, thanks.
You're welcome. All right, so the thing I wanted to show you all, as part of your pre-processing, you can get this image data generator object, and you can see here, and this is basically a way that the computer can read images that are saved on your computer or on Google Drive, and I'll talk through that probably during an office hour or maybe tomorrow. I'll have to see what, okay, never mind. Yeah, this week or early next week, I'll talk about it. But here you see that using this object, I can rescale my images. The flow from directory is just, where I'm getting my images from my computer. And I can tell it what my target size is, so you can actually rescale the image too. And this also determines your batch size. Let's just see if this is done running. Oh, nice, looks like it is. Well, you can see that my accuracy is pretty much as good as random guessing. And yeah, NaN loss function, this, well, it looks great, but you can see that this is only 0.1 accuracy. This is definitely not enough layers. Where is that? Yeah, this is definitely not enough layers for, especially for a 10 class problem. And also with such a low resolution of your images. As an example, I can show you all here. I don't know if I have any examples, but this was my image classification project, and the number of layers I had here. Oh, I guess I am going to talk about something else tomorrow using pre-trained network. So this is using a bunch of already existing layers, and on top of that, I'm using 1, 2, 3, 4 more layers. Let me see if I have that cell here. Yeah, I guess not, but it's already using a bunch of existing layers. You can see my archives of this. This is without that. These did not predict well at all. So yeah, I don't want to get into that, into my old project. Any other questions on convolutional neural networks or anything I've talked about today? All right, well, tomorrow I'm going to talk about transfer learning, again, using pre-trained networks, which is what I did in my project. Basically, what it is a bunch of companies have pre-trained convolutional layers and other networks too, to already be able to detect certain patterns. And then all you have to do is feed in your training data and add a few more layers after that. So it will basically make it a lot faster. Also, I'll do an overview of recurrent neural networks and the possible application to time series, and also text generation. I'll talk about how you can do something like grid search for neural networks, and then also how you can save your neural networks just in case you want to use them somewhere else. So for example, I did very briefly talk about pickling your scikit-learn models, but with neural networks, you probably don't want to keep retraining your models over and over again. So it is very helpful to be able to save your model and maybe use it in a different notebook where it won't like exceed your runtime. Any final questions before we break off for today? Awesome. Well, please vote on the poll just to indicate what project you want to do. Thank you to those who have already done so. I will later today assign a few project pairs for the people who have voted. And if you haven't voted, I will Slack you and hound you about that. All right, any final thoughts? All right, then I will talk to you all tomorrow. Any questions as usual, feel free to let me know. All right, bye everybody. Have a good rest of your day.
Thank you.